Welcome back to our series on different types of proofs. Today we're going to be looking at proof by induction. Okay, and proof by induction is useful for proving statements like this, right? This claim here says, for every integer, right, that's what this symbol means, n element of z. For every integer, if you cube that integer, and then add 2 times that integer to that result, you will get something that is divisible by 3. In other words, no matter what n you pick, 3 will go into this evenly. Now, if you want to take a few moments, try testing this in your calculator. Pick a couple different integers and then cube it and add 2 times itself to that and see if 3 goes into it evenly. If you did that, you'll find that it works for every integer that you picked. And if you do that enough times, you might convince yourself that this really is true for every integer, but that's not the same thing as an airtight proof, right? How would we prove that this is really true for any integer that you could pick, especially since there are an infinite number of integers? You could never test them all, right? Well, we're going to use induction to do this. And the proof by induction has 2 basic steps, okay? The first step is to show that the claim over here. Show that the claim is true for a specific integer. Right, very often 0 or 1 or something like that, right? But we're going to show that this works for a specific integer first, okay? Then the next step, and this is kind of what makes the whole thing work. The second step is we're going to show that if it's true for some integer, it must be true for the next biggest integer. Okay, so let's show that if true for some integer n, let's say, then it must be true for n plus 1. Okay, so this is an if-then statement that we need to prove, right? If it's true for some integer n, then it must be true for n plus 1. And hopefully you can see the intuition behind why this works, right? We first show it's true for some integer, like say 0. And then we show that if it's true for one integer, it's true for the next biggest one. If you show those 2 things, well, we already showed that it's true for 0, so then it must, since this second part is also true, it must also be true for when n equals 1. But if it's true for n equals 1, then by the second part again, it must be true for when n equals 2. And so then you can see how you get through all the integers like that. It proves that for any integer, it will always be correct, for any integer greater than the one that you started with, at any rate. So let's go ahead and prove that this statement is actually true. All right, so we'll start. I'm going to start by showing that it's true for 0, right? Okay, so step 1. It's true for 0, right? Because 0 cubed plus 2 times 0 equals 0. Pretty simple. And 0 is divisible by 3. So it's true for n equals 0, right? True for n equals 0. Now, step 2, okay, now we need to prove this second if-then statement. All right, so this step always involves assuming it's true for some generic integer, right? Or some arbitrary integer, right? So we'll say, suppose this claim is true for n equals k. Right, okay, so just some integer k, right? Then k cubed plus 2k is divisible by 3, right? Okay, we're just assuming that this is the case. Now, for the next part, right, we're going to see if this implies, we want to show that this implies it's true for k plus 1. So now let's look at k plus 1. So for n equals k plus 1, then we have k plus 1 cubed plus 2 times k plus 1. Okay, so you see all I did is I plugged k plus 1 in for n here, right? That's all that I've done so far. Now what I'm going to do is I'm just going to do a little bit of algebraic manipulation, right? So this here, I'm kind of running out of room a little bit, but stick there. Right, this here will eventually FOIL it out. It'll FOIL into this, right? You could just use binomial theorem to show that, or you could just do the work, right? Just FOIL this out and multiply it by itself 3 times. It's not too bad, but you'll eventually get this. And then I'm going to distribute the 2. Okay. Now, look at what we have here. What I'm going to do is I'm going to group these things in a certain way, right? I'm going to group the k cubed with the 2k. Okay, and then I'm just going to add the 1 to the 2 here and leave everything else as it is. So 3k squared plus 3k plus 3, right? So now, look at how this works out. This is divisible by 3 by our assumption, right? We assumed that this was divisible by 3 up here. So this part is divisible by 3. And then these are all obviously divisible by 3 as well. So what that means is this whole thing here is divisible by 3. So what we just did is we just showed that if it's true for some integer k, right? If this is divisible by 3 for some k, integer k, then it's also true for k plus 1, right? This must also be divisible by 3. And so now we've completed both steps of the proof. At this point, we could, maybe just step over here. Maybe just mention that's divisible by 3, and then it's customary, to write something like by induction, n cubed plus 2n is divisible by 3 for all n greater than or equal to 0. Right, so because what I just did is I used induction to show that this claim is true if n is an integer 0 or greater. Technically, I'm not quite finished yet, right, because I claimed it was true for all integers, even the negative ones. But that's relatively simple to demonstrate at this point by just remembering if I plug, negative n in here, right, a negative integer, then this algebraically simplifies to negative n cubed minus 2n, or negative n cubed plus 2n. So since we showed that it will work for this no matter what integer it is, it will obviously work for negative 1 times that. And so that that's sufficient to demonstrate that this is true for all integers. Right, so you no longer have to rely on just testing it in your calculator until you're convinced that it's true. Now you can know that it's true for any integer. All right, so that's just one example of proof by induction. Next time we'll look at another type of induction that's actually equivalent to this one, and we'll go over some of the ways that that could be useful as well. Thank you.